They came to Calumet, looked the situation over, opened up 18 shafts on Mine Street, and started to mine copper. They formed 4 companies. In 1869, they merged the 4 companies, forming the great Calumet and Hecla Mining Company. They worked on. In 1900, the great Calumet and Hecla opened 9 more shafts on the amygdaloid lode. Also, the famous Red Jacket shaft, 6-compartment shaft that went down 8,100. They mined copper from that depth, brought it to surface, put it into railroad cars, shipped it to the mills at Lake Linden. The copper was separated from the rock. The copper shipped over to Hubbell to the smelter. It was smelted there, made into ingots, bars, or cakes. And at that time, the Calumet and Hecla owned Wolverine Tube in Detroit. They shipped their copper to Detroit to the Wolverine Tube Company, and of course the Wolverine Tube made their copper tubing from the Calumet and Hecla copper.
The magic of the word copper has stirred and motivated man for centuries. The history of this metal is bound up with the history of human progress. This renowned metal is produced by Calumet and Hecla Incorporated and later fabricated by the Wolverine Tube Division. These products are the result of endless research and untiring effort to produce the finest in seamless tube. Let us go to the fabulous copper country of Upper Michigan, where copper has been mined for over 100 years. On the Keweenaw Peninsula, which juts into Lake Superior, is located the most important deposit of native copper ever found. New discoveries of the ore constantly stirred the pulse of those who lived and died here in the quest for native copper. The old Cliff Mine, founded in 1843, was the first successful copper mine in the district. It had a vertical shaft of considerable depth. Most of the copper was in large masses. From these early days have grown the well-regulated mines of today, with modern equipment replacing the pick and shovel methods of long ago. Since the days of the prospector, the speculator, and the adventurer, these people have remained loyal to the Keweenaw Peninsula, their home. The mines are their livelihood, their challenge, their work, and amid this scenic beauty, they live. Let us trace the development of various copper products from the time man first removes the ore from the ground until it is ready for use by the peoples of the world. Our story begins by going into one of the modern mines of today.
The men are getting into the man car, or cage, as it is often called, preparatory to going underground. The engineer on the surface controls the raising and lowering by means of long steel cables. The car holds 39 men and travels about 900 feet per minute, which is comparable to the speed of express elevators. As we proceed into the depths of the earth, our first observation is the supporting timbers. Some of these timbers are as large as 10 by 12 inches, depending upon the weight that has to be supported. Most of the shafts incline 31 to 38 degrees from the horizontal. Some of the mines have a vertical depth of over 1 mile. The temperature at this depth is about 91 degrees Fahrenheit. As the man car continues its descent, it passes level flats. Notice here the mass of copper protruding from the ceiling. The green-colored rock on the top of the shaft indicates the presence of copper. The man car stops at each level, and the men working on that level leave the car and walk or ride to their place of work. The mines are clean and well ventilated. Working conditions are not affected by outside weather. There are no dangerous explosive gases, and every safety precaution is taken. The copper ore is deeply embedded in rock and must be blasted out. Approximately 30 to 36 holes are drilled prior to charging and blasting. The drift miners use jumbo-type drills operated by means of compressed air. The holes are about 1 1/2 inches in diameter. In the drift, the newly drilled holes are charged with 60% dynamite. The small wires protruding from the holes are attached to electric detonating caps. These caps have different speeds of detonation, for it is important that all blasts do not occur at the same time. The cap and the attached wire are embedded in the first stick of dynamite. Additional dynamite is placed in the hole and tamped with a wooden pole. The two copper wires are called an aerial. One side of the detonating cap is wired to the negative wire and the other side to the positive. A knife switch is connected to the aerial and to the source of power. The closing of the circuit permits the electrical current to detonate the caps, and the explosion results. The power loader has replaced hand shovels. This mechanical loader, operated by compressed air, is capable of picking up 1/4 of a ton and loads a 5-ton car in about 3 minutes. In the old days, it took 2 miners and 2 trammers or muckers an entire shift to drill, blast, and muck up 2 to 4 feet. Because of this loader and other mechanical equipment, 2 men can handle twice that amount per shift. This miner is working on an inclined excavation called a stope. It is cut on the same angle as the shaft and follows the ore body. He drills as many holes as are necessary to break off the ore. During a single shift, 10 to 15 holes are drilled. 7 to 10 sticks of dynamite can be placed in each hole. The white rock is calcite and quartzite. Instead of detonating caps, fuses are used to time the explosion. Again, it is important that all the blasts do not occur at the same time. Therefore, the fuses are cut to different lengths. They will burn at the rate of 2 feet per minute. The fuses are lighted with a spitter which resembles a 4th of July sparkler and burns at a predetermined rate of speed. When the spitter has burned out, the miner knows that it is time to leave the area immediately. Blasting breaks up the ore, which falls in small pieces on the incline. An electric or air-powered engine pulls the scraper by means of long steel cables. The broken ore falls through the chute into waiting tram cars, which are drawn away over narrow-gauge railroad tracks by a battery-powered locomotive. The operator is known as a trammer. When the tram car arrives at the shaft, the trammer dumps the load. The ore falls through the chute pocket into a skip. The skip is held just below the pocket. When the skip is full, it is pulled to the surface for dumping in the rock house. When the skip emerges from the mine, it is drawn up into the rock house. Then the 5-ton load is dumped into a large pan. This is raised, which feeds the ore into a giant rock crusher. The rock is crushed to a maximum size of 4 inches before it leaves this machine. The crushed rock drops into large storage bins. At regular intervals, The bins are emptied into railroad cars. Poor rock, which is ore containing little or no copper, is discarded. A diesel locomotive picks up 12 to 15 loaded cars at the rock house. Each car holds approximately 50 tons. They travel 8 miles to the stamp mill. Here again, we see the beauty of the Michigan North Woods. It is not uncommon to see deer, partridge, and other forms of wildlife along the right-of-way. The cars enter the top of the concentrating mill, where the ore is dumped into bins. The flow of ore to the stamp is controlled by an operator. Large chunks of copper, which might fill the mortar and impede the action of the stamp, are picked out. The rock is crushed to a 5/8 inch size before it can leave the stamp mortar. It is further screened to 3/16 of an inch and returned to a crushing roll. The first concentrating is done on jigs, which separate the heavy copper from the light sand. When the sand leaves the jig, it still contains some copper. So it is ground by means of a ball mill, which is filled with 3-inch iron or steel balls. A screw-type classifier in a closed circuit with the ball mill controls the size of the fine sand being conveyed to the flotation process. The finely ground sand and copper is mixed with oil and agitated to create bubbles of various sizes. The oil bubbles pick up the copper. Although the sand is lighter than the copper, it is heavier than the bubbles, and as a result, the sand sinks to the bottom of the machine while the copper-coated bubbles float on the surface. When skimmed into settling tanks, the bubbles disintegrate and the copper settles to the bottom. From here it is conveyed by a drag belt into a suction filter which reduces the moisture in the flotation concentrate. Then it is sent to concentrate cars for transportation to the smelter. The waste sands or tailings from the flotation tanks are conveyed by water through a sluice and deposited in a lake. The concentrates are transported to the smelter where they are dumped into a receiving bin. The concentrate is mixed thoroughly with coke or coal screenings. The blended concentrate then is moved to the furnace. Through the center of the roof, the concentrate containing 40 to 75% copper is loaded into the melting furnace. This reverberatory type coal-fired furnace has a capacity of approximately 1 million pounds. In the slagging operation, or removal of the molten gangue from the smelted material, the slag runs into a stream of water, which granulates it and permits it to be pumped out as waste. He breaks away the clay from the tap hole so the metal can run freely. A sample is removed from the stream by a tapper and is poured into a mold to be sent to the laboratory for chemical analysis. The molten copper runs down a trough between the melting furnace and the refining furnace. The temperature is above 2,000 degrees Fahrenheit. It takes about 1/2 hour to transfer 400,000 pounds of copper from the smelting furnace to the refining furnace. In the refining furnace, the copper is agitated with compressed air. The oxygen of the air combines with the impurities to form slag. The men are skimming the slag from the surface with rattles. It is also granulated, but being fairly rich in copper, it is pumped into a concentrate storage building. A sample of the metal is taken and allowed to solidify. By observing this change, the state or condition of the molten bath can be determined. To help deoxidize the molten copper, a green hardwood pole is placed in the metal. This is a procedure modern science has never improved upon. The metal is being tapped from the huge refining furnace into a 9-ton oil-fired transfer ladle. Here again, a green hardwood pole is put to use. When the ladle is fired, oil flames coming from the stack and spout are visible. A 25-ton tilting furnace receives the contents of the transfer ladle, and the flow of metal to the casting ladle is controlled by this large tilting furnace. Phosphor copper is weighed out and used to remove the last remaining oxygen from the metal. The phosphor copper is added to the metal in the ladle and mixed by means of small hardwood poles. A layer of charcoal is maintained over the molten copper in the ladle to prevent the introduction of oxygen during casting. On top of the water-cooled molds, a strainer box is placed, which controls the rate at which the molten metal fills the mold. To assist in the removal of the billet, the mold is painted with a mixture of oil and bone black. The billets, having solidified, are dumped through the bottom of the mold into a water quench. A conveyor raises them to a preliminary inspection belt. The billets that pass inspection are cut on a high-speed saw to specified lengths. From time to time, short lengths are cut for use as samples by the laboratory. A laboratory representative imprints charge numbers on the samples, then takes them to the laboratory to make a chemical analysis. In the laboratory, each charge must be tested to ensure that the necessary physical and chemical requirements have been met. In the billet casting, the addition of phosphorus has removed the oxygen. Tests now must be made to determine whether or not the phosphorus content is too high. An excessive or inadequate amount of phosphorus can seriously impair the life and workability of a copper product. Battery assay test, phosphorus determination, titration. These are but a few of the types performed, some of them requiring 2 to 3 days to complete. But without the information gained, there could be no control over the quality of the metal. Therefore, complete reference records are made and maintained on all tests performed. The ends are carefully inspected to be sure they are not porous, and the surface is checked for imperfections. These are removed by grinding. A die mark is made to identify them in the event reference is made to their chemical content. After weighing, the cars leave the scale house and move to the loading and storage platforms. We have followed the processing of copper ore through all the various stages until we see it now in billet form, ready for shipment. The billets have been subjected to rigorous inspection at every stage of their development and now represent the wealth of experience gained through 80 years of copper mining and smelting. Their quality has been controlled throughout their formation, and as a result, further fabrication and development will be greatly simplified. They will travel over 600 miles from Calumet to Detroit, where they will be further processed by piercing until a base tube is formed.
This is our destination, Detroit, Michigan, and the Wolverine Tube Division, a unit of Calumet and Heckler Incorporated. The main office and large primary mill producing non-ferrous tubing is located here. Copper and many alloys of brass tubing are produced. Much of this material is further processed into a multitude of fabricated parts. Wolverine's constant aim is to make quality products. A trainload of copper, soon to become seamless tubes, and other tubular products arrive from Calumet.
The billets are unloaded and placed on a conveyor which carries them inside the plant. Although rigid inspection controls are maintained at the smelter, another check will be made here. A sample of this load will be tested in the Wolverine laboratory, the first of many tests made. To assist in the removal of the billet, the mold is painted with a mixture of oil and bone black. The billets, having solidified, are dumped through the bottom of the mold into a water quench. A conveyor raises them to a preliminary inspection belt. The billets that pass inspection are cut on a high-speed saw to specified lengths. From time to time, short lengths are cut for use as samples by the laboratory. A laboratory representative imprints charge numbers on the samples to make a chemical analysis. In the laboratory, each charge must be tested to ensure that the necessary physical and chemical requirements have been met. In the billet casting, the addition of phosphorus has removed the oxygen. Tests now must be made to determine whether or not the phosphorus content is too high. An excessive or inadequate amount of phosphorus can seriously impair the life and workability of a copper product. Battery assay test, phosphorus determination, titration. These are but a few of the types performed, some of them requiring 2 to 3 days to complete. But without the information gained, there could be no control over the quality of the metal. Therefore, complete reference records are made and maintained on all tests performed. The ends are carefully inspected to be sure they are not porous, and the surface is checked for imperfections. These are removed by grinding. A die mark is made to identify them in the event reference is made to their chemical content. After weighing, the cars leave the scale house and move to the loading and storage platforms. We have followed the processing of copper ore through all the various stages until we see it now in billet form, ready for shipment. The billets have been subjected to rigorous inspection at every stage of their development and now represent the wealth of experience gained through 80 years of copper mining and smelting. Their quality has been controlled throughout their formation, and as a result, further fabrication and development will be greatly simplified. They will travel over 600 miles from Calumet to Detroit, where they will be further processed by piercing until a base tube is formed.
This is our destination, Detroit, Michigan, and the Wolverine Tube Division, a unit of Calumet and Heckler Incorporated. The main office and large primary mill producing non-ferrous tubing is located here. Copper and many alloys of brass tubing are produced. Much of this material is further processed into a multitude of fabricated parts. Wolverine's constant aim is to make quality products. A trainload of copper, soon to become seamless tubes, and other tubular products arrive from Calumet.
The billets are unloaded and placed on a conveyor which carries them inside the plant. Although rigid inspection controls are maintained at the smelter, another check will be made here. A sample of this load will be tested in the Wolverine laboratory, the first of many tests made during the processing of the tubing. Only by checking and rechecking in this manner is the final product truly quality controlled. An examination for porosity and other surface defects is made on all billets used in the piercing method of manufacturing seamless tubes. After inspection, the billets are loaded into a furnace where they are heated to a temperature of approximately 1600 degrees Fahrenheit. When the heated billet emerges from the furnace, it drops into position in a large piercing mill. It is forced between two inclined driving rolls, which break a hole ahead of a pointed mandrel and rod. The mandrel irons the inside surface. This action forms a seamless base tube. They are cooled in a water-quenched tank and made ready for the subsequent operations. In order that the end of the tube can be inserted into a die to permit further reduction, it must be pointed. A squeeze pointer, which exerts pressure up to 600 tons, is used for this operation. After the tapered point is formed, the tube is ready for the drawing operations. Before moving to the drawing operations, let us follow the production of seamless tube by the extrusion method. Copper ingots are taken to a casting shop where they will be combined with other metals to produce various alloys. Correct scientific casting is extremely important in the preparation of quality metal. Furnaces are charged with metal, thoroughly mixed, and heated to the proper pouring temperature. The molten metal is poured through a strainer box into a water-cooled mold. It controls the speed of pouring and traps impurities, which is important in making sound casting. While the heat is being poured, the caster secures a sample. The heat number is stamped on the sample, and it is sent to the laboratory for chemical analysis. The sample is drilled, and the drillings are weighed, then dissolved in acid and titrated or electro-deposited to determine the copper content. This test is always completed before another heat is poured. By this method, the composition of the cast metal is immediately determined and any necessary adjustments can be made. Constant care must be exercised to make certain that the residual phosphorus content of copper is held to specific limits. The colorimetric method is used to determine this minute quantity. These are but a few of the many tests used to control quality. After the sample has been sent to the laboratory, the remainder of the heat is poured. 3 billets are cast from each furnace heat, and their total weight is approximately 1,000 pounds. After the billets have cooled sufficiently, they are removed from the molds and are conveyed through a water quench to a saw. Here they are cut to a predetermined length, and the surface skin is removed by means of a scalping operation. This practice ensures a clean billet free of surface imperfections and carbon, and as a result, a better tube will be formed. The practiced eye of an inspector appraises the machined billet, checking not only the ends, but the entire surface. Only billets entirely free from defects and approved by the laboratory will be further processed. A stockpile of billets is maintained to ensure a backlog for continuous tube production. From this reservoir will be drawn the necessary billets to meet planned production requirements. The preheated billets pass down a roll conveyor, and the operator drops them into a container. An upsetting tool is used to center the billet and seat it firmly in place. This prevents any rocking movement during the extrusion operation. A pointed mandrel pierces a hole through the hot billet. Then the main ram, under a pressure of 3,000 pounds per square inch, forces the metal between the mandrel and die. From outward appearances, the tube is formed as easily as toothpaste is squeezed from a tube. In this operation, the mandrel picks up considerable heat, and as a result, an oil bath is used for cooling. The extruded seamless tube drops into a pit below the extrusion press. Here, the red-hot tube is grasped in tongs by the pitman and straightened. Then it is dropped into a water quench, where it is picked up by a conveyor and raised to an inspection rack. Our billet has now become a seamless tube. After extrusion, the tube is inspected for uniformity of wall thickness. The variance in wall thickness must be within established tolerances. The tubing is also examined for surface defects, which may have developed during the extrusion operation. By constant checking and inspecting at each stage of production, quality standards are maintained and costly rejections are prevented later on. Our extruded tube also must be pointed to permit drawing. The rotary tight pointer is used for this operation. Tubes are held firmly in place by means of a hydraulic clamp while being pointed. The pointer is powered by a motor-driven flywheel which revolves around a set of rollers. These rollers impart a hammer action against a set of formed dies, which in turn point the tube. The major function of our tube mill is the actual tube reduction, or drawing, as it is commonly called. Commencing with seamless tubes from 3 to 4 1/2 inches in diameter, they are reduced in size and wall thickness by successive drawing operations until they meet a customer's specific requirements. Because the energy required for drawing varies with the size of the tube, many different sized draw benches are used. In an effort to ensure the finest quality, our tubing is subjected to a scalping operation. This is a decided advance in controlled quality tube production. A thin layer of the outside surface of the tube is removed, and as a result, any imperfections on the surface are erased permanently. If such action is not taken, defects almost invisible to the eye may become covered during the drawing operations, and a tube of inferior quality would result. During the drawing operations, the tubing increases in length to such an extent that it cannot be handled conveniently. An automatic saw is used to cut the long tubing into predetermined lengths. As a result of the preceding operations, the copper has become work-hardened or less ductile. In order to increase its workability, it is necessary to soften the metal. This is accomplished in a controlled atmosphere furnacer. Oxidation of the metal during annealing is prevented. The result is a clean, bright tube that needs no cleaning or pickling. To determine the degree of softness, a grain size test is made. A sample is polished and the surface etched with chemical reagents. The grain structure is examined through a microscope and compared with a standard chart of grain sizes. The tubing now has been made ductile enough to permit further reductions in size. The basic method for all bench drawing is the same. A drawing mandrel fastened to the end of a long rod is placed within a tube. The tube containing the mandrel is grasped by tongs on a drawing carriage, and the entire tube is pulled through the die and over the mandrel. The die controls the outside diameter, and the mandrel the inside. At frequent intervals during the succession of drawing operations, a process inspector checks the dimensions of the tube. He is particularly concerned with uniformity of wall thickness, outside dimension, and tube roundness. This periodic inspection ensures the production of tubes to close tolerances. As the drawing continues, the size of the point remains the same. It becomes necessary to repoint the tube to permit its introduction into smaller dies. This operation occurs frequently throughout the drawing operations. As the result of progressive reductions in size, the appearance of the tube changes materially. It becomes so small that chrome-plated wire is used as a drawing mandrel for holding the inside dimension. And so, from a solid block of pure copper, and as the result of many separate and distinct drawing operations, we have now produced a capillary tube. This unique series of tubes, the smallest of which has an inside diameter of only 26 thousandths of an inch. Truly an engineering accomplishment. Because of the drawing operations, the tubing does not remain completely straight, and to correct this condition, it is run through various types of straighteners. It passes between adjustable angle rolls, which remove the camber and retains the uniform roundness of the tube. All tubing is supplied commercially straight. Tubing also is straightened on a roll-type straightener by passing it between a series of rollers. The principle of this type of straightening is to remove the long camber by a series of short bends. Small tubing is handled in a similar manner. The selection of straighteners is of utmost importance depending on the particular application of the finished material. The straightened tubing is cut to specified lengths in accordance with each customer's requirements. Both circular and band-type saws are used. Great care must be taken in the design and construction of the saw blades in order to minimize burrs and ensure a clean, square cut. Because customers request a specific hardness in their finished tubing, an additional test must be performed. A prepared sample is subjected to a Rockwell hardness test, which indicates both normal and superficial hardness values. Tests also are conducted to determine the tensile strength, yield point, and elongation properties of the tubing. Samples are given an expansion test by forcing the tube over a tapered mandrel. These and many other tests determine the fact that the complete requirements of the customer have been met. The finishing operations on capillary tubing are most exacting. Because this tubing will be used for restriction and control purposes, tolerances must be held very closely. Inspection must be rigid so that quality control may be maintained at all times. This tubing will become an important part of some manufacturer's unit, and uniform quality must be assured. In spite of every precaution during sawing, a slightly rough edge is left. A precision chamfering machine cleanly removes this. Each length of capillary tubing is washed on the inside with a cleaning fluid. Because the liquid is passed through the tube under pressure, any excessive restriction is easily noted. After the tube is thoroughly washed, air is forced through the tube to completely dry the interior. Reputations of many units in the refrigeration field depend on the consistent quality of this tubing. The capillary tube is then air tested to ensure that the flow characteristics as specified by the customer have been obtained. The tubing will then be bundled and the ends carefully covered prior to shipment. Returning to the production department, we follow another method of tube drawing called bull blocking. By this method, the tubing is plug drawn to a smaller size and at the same time coiled. When the finished coil is removed from the bull block, it is sent to a trim saw. The tube is cut at an angle, which permits inspection of the inside surface. Some customers desire that their tubing be shipped as coils. In this form, they are easier to handle, easier to ship, and more convenient to store when received. In order to obtain a softened tube with the proper grain size, the tubing must be annealed prior to shipment. Air is purged from the coils and replaced by a gas to prevent oxidation. They travel through an atmosphere-controlled annealing furnace, and their rate of travel depends upon the temper and grain size desired. The coils move to a saw, where they are again trimmed to permit inspection of the inside for cleanliness. All refrigeration tubing is pressure tested underwater. To permit this test, one end of the tube is crimped and dipped into a flux and molten solder. The open end of the tube is placed in a testing nozzle. The coil is submerged, and an air pressure of 250 pounds is applied. If the coil passes this test, the other end is then closed to prevent the introduction of dirt or moisture and to ensure a clean, bright tube for the customer. The coil is placed on a conveyor and given a final surface inspection before shipment.
One of our recent developments, the Wolverine spun-end process, is a revolutionary method of closing, reducing, or otherwise forming the ends of tubing. This permits the formation of a multitude of fabricated parts to very close tolerances. There are many possible applications for this type of product. Tubing also is formed into various shapes on a coiling lathe. A mandrel is used so that the tube does not flatten. A wide range of sizes may be coiled in this manner. Large oval coils and other shapes may be formed on this special bending machine. Another Wolverine development is TrueFin, the integral finned tube. The fins on this tubing are actually extruded from the wall of the tube. TrueFin has many applications in the heat transfer field, for it greatly increases the surface area of plain tube and yet is capable of being bent and formed into various shapes. During the manufacturing operations, oil or other lubricants must be used. These substances must be removed before the material can be shipped. The parts emerge from the bath completely clean and dry. Although process inspectors check the tubing at every stage of its development, a final inspection is made to make certain that customers' specifications have been met. A heavy responsibility for the maintenance of quality standards falls upon the inspection department. Each tube and fabricated part is subjected to rigorous visual and physical tests. This constitutes a never-ending vigilance to ensure that the tubing which leaves the Wolverine Tube Division is representative of the best quality for the purpose for which it is intended. The inspection department plays a major role in maintaining the inherent part of Wolverine tube production, quality control. When the coils arrive at the shipping department, they are arranged, tied, and packed to prevent damage during shipment. The cartons are clearly marked to indicate size, length, and type of material. This method of packaging can prove very helpful for the distributor or jobber. Care must be exercised in the preparation of straight lengths for shipment. The stock must be weighed and an adequate shipping list prepared. Strong wooden boxes secured by steel straps guarantee safe delivery of the material. Complete information regarding size, length, and type of material is stenciled on the outside of the box to enable the customer to sort and store the product. Approximately 60% of the shipments are made by fast motor freight and the remainder by rail. Prompt shipment is appreciated by the various firms using Wolverine products in the manufacture of equipment and appliances. Quality control has been thoroughly exercised throughout the development of the product. Let us now view some of its specific applications in the various industries. Wolverine tube is used in the manufacture of many products of such diversified nature as fire extinguishers, door chimes, spray guns, and many others. The significant differences in cleanliness and dryness of restrictor tube, fabricated parts, and spun tube assemblies assume dependable performance for refrigeration. Through extensive research, Wolverine TrueFin and other tube products pack maximum efficiency into minimum space in heaters, coolers, and air conditioning units. Our brass pipe and copper water tubing assures uniformity in size well within the required specifications. Petroleum and chemical processing plants depend upon the ability of copper and brass tubing used in condensers, oil, and gas lines to resist corrosion. Through all the phases of the mining and fabrication processes, we constantly strive to better serve the industries of America by maintaining quality control from ore to finished product.
The only one like its kind in the area. 6 compartments that went straight down. 3 to hoist rock. 2 for men, 1 a spare. 4 hoisting engines. Chap until 1968, until the strike shut us down. After that, the Home State Mining Company came in and probed here. They worked for a couple of years, but didn't find it feasible to operate because the copper price wasn't high enough. So they left this area, and the area was shut down again. Well, since then, some of the
from the window I watched. My friends, they couldn't have been kinder. And my schooling was cut as I quit in the spring to marry John Thomas, a miner. Oh, the years passed again and the giving was good, with a lunch bucket filled every season. What with 3 babies born, the work was cut down to half a day shift with no reason.
and
the
idle
shaft
ever
was soon
since.
shut and more work was gone.
Former employees of Calumet and Hecla decided they would open the shaft, but somehow it didn't mature. And this shaft has been vacant. In 1960, they decided to open up two shafts on this lode, number 3 and number 6. That's when this shaft was opened. And they worked this mining company. The Schoolcraft Mining Company operated 7 shafts here in this area. In 1892, they shut down the whole operation. We don't know if they ran out of money or what the problem was. They couldn't sell their copper. But they did shut down in 1892. The Centennial Mining Company at that time purchased the property. And they turned all of the mining buildings into homes. At that time, there were so many people in the area they didn't have houses enough for them. So they turned the carpenter shop, the machine shop, the blacksmith shop, and all of these buildings into homes. My grandma ran a boarding house here. We were living in the old Schoolcraft pay office. Well, Centennial Mining Company just left the mines idle through the years. A hole in the ground. We could see the water. It was a fence around it. All of these shafts. The Centennial Mining Company, the other side of the highway, operated the amygdaloid shafts, 2 of them. And they worked those shafts till 1963 when they shut down. And they dismantled that property in 1965.